So what I want to do in this talk is give a slightly different perspective on the work of Koshikawa on the log prismatic site, and explain how using some stack theoretic techniques, you can really view it as a special case of the Bad-Lurie machinery. And so just a different perspective that where you don't have to develop the theory from the ground up, but can sort of pass to already the work of Bad-Lurie. So the central player is the stack of log structures. So let me start with that. So I don't want to, there are lots of experts here on many things. I do still want to review some of the basic theories. So let me start by making 4 definitions from log geometry that we use. Okay, so let me remind you. So a pre-log structure on a scheme X is the monoids M for the Ital in the Ital topology with a map of monoids which I usually suppress from the notation, but like that. And it's called a log structure. If you look at the pre-image of the units, this maps isomorphically to the units in OX. Okay. That's the first point, or first 2 points. To Kato. So a pre-log structure has an associated log structure which I'll denote with an upper A. It's not important really for me what the construction is. It's a suitable adjoint, but let me just write it out. You just fix the condition on the units. So you do some push out. And then, so that's number 3. The 4th point is that a log structure M is called fine if Ital locally of the form Ital locally associated to a map. So you take a constant monoid P, where P is finitely generated integral monoid. So that's the class of log structures that I'll be considering in this talk. Okay. It's a bit of notation. So if you have a log structure M, then you have the units sitting inside M by this isomorphism. And so the quotient, that's a sheaf of monoids, is M bar. And so, make a remark. Fine log structures are closely related to toric stacks. So here's an example. Well, I'll say it as a remark. So let's suppose we have a fine log structure. Look at M bar, and we have a map of monoids P to M bar, which I assume that it locally lifts to a chart. Meaning, I should have said that when you fix a monoid P and the log structure associated to a map like that, I'll call that a chart. Okay. And so if you think of, if you have this situation, think about the set of lifts of that map. That's a this is a torsor under the homomorphisms from P group to OX star. Because, I mean, this is monoid, so it's not an abelian category, but still you have the action of OX star on M. This is a quotient, so if you think about this set of maps up, that's a torsor. And from this, you see that a picture like this gives you, first of all, a D, I'll write it P group on group GM torsor. So if I start with the M to M bar and the P, then out of it I get torsor under that group scheme, which is, if you, the typical case, this will just be Z to some rank R, and so this is a copies of GM. And so you get a torsor T to X, group torsor. And then there's a bit more information, which is the map from M to OX. All right, and so if you have a lift here, you also get a map from P to OX coming from the map there. And so that turns into the equivariant map to spec Z monoid algebra P, which I'll maybe write A sub P. An equivariant map like that. And so now giving a torsor and an equivariant map, that's the same thing, or it's equivalent to giving a map from X to the stack quotient. And in fact, you can show that the stack classifies, you can view it as the moduli stack of log structures together with a map like this. Okay. And so there's a slide very well, maybe I guess that's the remote one. If you've never seen this before, a useful case is to just think about the case when P is equal to N, the natural numbers, in which case we're looking at the stack A1 on GM. And you can think of this stack as classifying line bundles L and a map to OX. So that turns out to be sort of a special example of the log structure. Okay, so here's a sort of generalization. So let's think about, so let me write log over Z. So this is the the stack over Z. This is the fiber category. Which sends X to the groupoid of fine log structures on X. So, I mean, this is a little bit sloppy, but it's the way I wrote it. It's not a fiber category, but okay. So, so I'll think about this. So this is a stack and a log scheme, which by definition is a pair consisting of a scheme X together with a log structure. That's equivalent to just a map topology. To give a map from X to this fibered category is just the data of the log structure on X. And now there's an old theorem, which is that this log is an algebraic stack. So the main point here of this lecture is there's this story here about the stack log, and I want to explain how just viewing log geometry as a relative theory relative to the stack, you can see the log prismatic cohomology as sort of the relative theory in this setting. I don't want to spend too much time on log geometry because I'll only use it in a certain formal way, but I'm happy to take questions. Okay, so what's the thing? So the key map, which is that this stack carries a lift of Frobenius over Z. And so I'll write it here. Which is if you have a log structure M on X, you can send that, so it's a sheaf of monoids, so you have multiplication by P. And you can send that, so you have that, and you can take the composition. And then you can take the associated log structure. And so, so this is a morphism of stacks. Over Z, and it reduces to Frobenius and so maybe let me see. Example. So look at something like this, A1 mod GM. You can guess what that lift of Frobenius is, because, or more generally, if you look at sort of a toric variety, it always carries a lift of Frobenius over Z. So okay, and so yeah, okay, and let me also just say we have the lift of Frobenius, and then let me also mention that there's a variant. So that's, I guess the way to think about it is the stack log that I've written here is sort of the absolute theory, and there's a variant, which is if you start with some base log scheme, and also write down relative version. Like this, the points are log structures. Sorry, f x to s, log structures mx of x plus that's sort of the relative version of this stack. So morphisms to this are log schemes over. So let's write it out. That data is the same thing as a pair. So a map x to s and a map from the pullback of ms to mx. All right. That's all the log geometry I need. You won't go far off if you just think about these toric stacks. Quotient of the AP mod. I just erased it. The AP module of the torus. And so let me do the log prisms. 26. Okay, so there are many experts here, so I'm slightly nervous talking about this, but okay. So what is a prism? So it's the following notation. So start with the ring. For me, it will always be p-adically complete. Some ideal, finding a Cartier divisor. And because I want to think of things geometrically, I'm always going to think about, so phi will be a derived lift. So this is this explained about Olsson, for example. But if the ring is p torsion free, I think a delta structure is the same as the lift of Frobenius, but in general, there's more work, but you can trace it as sort of the appropriate derived sets. So I'll just think about it as a lift of Frobenius interpreted correctly, and there are plus conditions, which I won't spell out. I mean, there's more. Yeah, is that okay? Okay, so what's the point? The point is that so when I think about the stack here, which will be the phase change this. This is again the absolute thing. And then it comes with this phi log across the phi. Maybe I should put a decoration A here. Which is the lift of Frobenius to this here, right? So A has a lift of Frobenius, has this ideal into ring. So now I get a stack, an ideal, and a lift of Frobenius here. And so this is, in some sense, I don't know what the term, I want to call it as prism stack, maybe. One of the experts. Is there a scheme version sort of yeah, anyway, it's this kind of structure, except we're over now an algebraic stack. Yeah, if it's okay, I don't want to. I mean, to be a prism, I mean, there's more to say. Yeah. Okay. Okay. So look, I'm going to use things in a very formal way. So I don't think it. So now the setup in this log prismatic story is, again, in the absolute setting for now, is if I give you a log scheme, mx, and over a bar, which is I, and here I view it the trivial log structure for now. I'll do the relative setting in a moment. I can view this as giving a picture like this. Right, so I have the reduction mod I give myself a scheme over the stack, which is a log scheme over a bar. And so this is right, this is the setup for the sort of usual story of log or of prismatic cohomology. You have a prism, and then you have a scheme X over the a bar, except in this case it's that stack. And so you get now. And I'll explain more about this, but we can do this. Setting of this is sort of as I'll explain what this is as defined. Don't worry. Or maybe Botschel, so I'm not sure where. Probably Botschel for this definition. But so you have a scheme X over the A bar, which when you view this as a prism, then you have the associated prismatic cohomology. Okay, I'll write out more about this, but maybe I'll state it as sort of a poorly worded theorem. What I want to say is that this recovers, I'll have to tell you the meaning of that. Cauchy-Powers log prismatic site. So if you think about the stack, log A as a prism, and plug it into the prismatic theory, you will get that. Okay, so let me explain that. So what is the site? Especially for people who are not familiar with this, so let me explain what it is. So, well, the objects, if you copy down the definition, it should be a delta ring, which, well, it's, think of it as a ring plus a lift of Frobenius satisfying some conditions. But it should be a delta ring over, and I should have given, sorry about this. Let me give a name for this, let me call it chi. Over the stack, log A. So what's that? 5B prism plus a morphism to X, and this should be a morphism over this log A bar. Okay, so of course I'm being quite sloppy here because log is a stack, so you have to worry about to say morphism. For example, a triangle like this means you also have to specify an isomorphism going across. And likewise here, what I mean is you have a lift of Frobenius to B over the lift of Frobenius here. And so you have to worry about higher categorical things. But,
so there's no non-degeneracy conditions? Like the only condition is that IB is the invertible ideal in B.
Let's see.
No, sorry.
I think I probably do want.
I'm just
no, I don't. I think I want it to be a prism over the base prism. Is that?
But
what's the non-degeneracy?
sorry, are these technical conditions like boundedness?
Oh yeah, I do want bounded p torsion and the bounded prism and. Yeah.
And are you always in the world of schemes, or are you going to allow formal schemes at some point?
Yeah. So in the end, I'm going to be looking at p-nil functors on p-nilpotent rings. So I want to think about formal schemes and so on. Yeah. Thank you. Yeah. Okay.
Right. I just had a question. So, is there an interaction between the log structure on G and the prism structure thing?
Say again?
So, sorry, is there some interaction between, like, so there's a log structure on B and there's lift of Frobenius? Is there some interaction there?
Yeah. So that's going to be my next comment. So the point is that it's over this lift of Frobenius here. Okay. And so, in fact, let me say this, that this is exactly equivalent to what Koshikawa calls a delta log ring. Maybe I should make this more explicit. Can be 5B over A plus strict. So if you write out what this means in terms of log geometry, and I know, yes, I'll try to do it. Okay, so maybe let me try to make this more explicit.
Can you read the last piece aussi?
Here?
Ja,
that
left
should
strict morphism and then
a strict morphism of log schemes from the reduction mod I to X mx.
What is a strict morphism?
So it means that, yeah, so let me flesh out. That means that let's say F pullback mx, I have too many F's, G, let's say, G upper star, that this should be isomorphic to specified isomorphism. So let me try to write out, and thank you for asking. So let me write out what this means. So we're supposed to have spec B map into this log A. Now, what is that? That's a log structure MB on B. And so then I'm supposed to have a lift of Frobenius by B. And then here's log A again. And here's my map. And then I'm supposed to have the chi here. And then I'm supposed to have, let me write it this way, an isomorphism between that arrow and that arrow. And I think this is where your question comes in, Akil. So what is that saying concretely? It's saying that if I take 5B upper star of this MB, that's supposed to be I'm supposed to specify an isomorphism with, well, let me write it out again. You take MB multiplication by P to MB B, and take the associated log structure. And so that's exactly, so again, now back to your comment, if it's, let's say we're looking at a p-adic formal scheme, you know what the pullback by Frobenius of the log structure mod P is this one. And so you see that if you're going to have a lift of Frobenius as a log scheme, you have to specify an isomorphism between the pullback of these two log structures. So at least in the P torsion free case, this is exactly a lift of Frobenius as a log in the log setting.
In the log setting, is there also kind of a point of view on the delta log ring that derived lift of Frobenius in some sense?
Yes, and it's a little easier than how thorny you might think the problem is, because, I mean, again, this is back in the Bott-Schulze paper. There's this argument about W2 being the pullback of when you look at you draw a diagram, and so you can, which gives you a push out. There's a, yes, the answer is yes. Thank you for the questions. All right, so
sorry.
Yeah.
Sorry, I have maybe a very naive question. So where I mean in some sense, I mean you impose this log instead of pre-log, and I'm fine. If I understand correctly, it's you just used to see that this log thing is an algebraic stack, but you can also have a pre-stack, I guess, a pre-stack to classify pre-log structures, and that this formalism, I mean.
I think up to now that probably works, but now what I really want to do is then use known results to deduce theorems in this context rather than derive them from scratch. So, you know, I want to do things like hypercover of this algebraic stack and get some descent properties and things like that. So yes, I think right now it's very formal, and you could try, well, you need log structures, I think, because otherwise sort of this interpretation doesn't work, but
Sorry, is it possible to say concretely what this means? Like if I have an actual chart,
yeah.
what condition is this on the monoid mapping into the ring? Is it literally saying that pi axis p powers, or is there some fuzziness allowed?
It's specifying an isomorphism. Yeah, there's, I mean,
so if it's a log structure described by a divisor, are you saying that Frobenius pullback of the divisor is p times the divisor?
In that case, I think the isomorphism is unique. So yes, I think that's right. Yeah. But in general, you know, you have to specify the data of this isomorphism.
So I sort of have a similar question to what was previously asked. Okay, so I mean, I guess assuming we are looking at log structures, the definition of log A, there's still this fineness condition.
Yeah.
And I guess it's not completely clear how that's sort of reflected in this correspondence. Like, for instance,
all my log structures at this point are fine. I should have said it.
I see. Okay, so if
Okay. Make a remark. So once we have this interpretation of this delta log ring, so I'd really just think of it as a sort of delta ring over this stack. Lift of Frobenius in that way. So let me. I give you following Koshikawa, let me call this maybe a delta log prism, meaning it's a prism. And then we have this lift of Frobenius on the log structure too. And so that means we have this kind of picture. This is the original. In this situation, you can sort of relativize the construction of this map chi to also get a map here. Maybe I should have said, if I call this, probably introduced this earlier, let me call it, if I call this M sub B P, so then this data here is an isomorphism phi A over star M sub A M sub P. Then you just use the same map, M goes to M sub P, and that'll define for you a map of stacks here. And so if you now write out, you can now take Prismatic Cohomology, that is X over A, so this is 4 X and X over stack the bar R. And you get this prismatic cohomology, and this agrees.
Sorry, have you said what the topology on the cycle is?
I have not. So maybe, yeah. Well, I guess there's two ways. One is to, I guess you could do probably, well, I think you could do a tau topology. You could probably do FPQC topology even. I think you could also do no topology and take appropriate limit over the whole category. And I also didn't tell you morphisms. I have lots of things I can tell you. Right, so, the sort of summary statement is that in this sort of log situation, you can view it as sort of the usual theory of prismatic cohomology, but viewing this as sort of the base principle. That's the summary. Okay. What is the stopping time, Jacob? What time do we stop? Just so I can keep track. 11. Okay. All right. So let me talk about the stack. So I'll discuss prismatic theory, but you could, for the experts, could also consider filtered version for those who know. So let me recall. Drinfeld. I think I first learned it from watching a video that Drinfeld gave in this room, if I'm not mistaken. Okay, so X p-adic formal scheme. So then prismatization, which is going from p-nilpotent rings to cuboids.
Sorry.
Yeah.
I made some assumptions in previous comparison theorem. I mean, what assumption on X?
Okay, so-
smoothness, whatever. I mean,
Sorry?
I mean assumption like smoothness. I mean,
No, I don't think I need that for this because I'm doing the site version and actually the sites are literally identified.
okay.
But later, when I want to compare with crystalline cohomology, things like that, I need some assumptions.
Okay.
Okay, but this is really a translation of what it means to have a lift of Frobenius over the stack. And you recover really the notion of a delta log, right? Yeah.
This cohomology theory, what is the source of this cohomology theory? Where does it take place?
Here?
Yes.
Well, I guess the way I wrote it, it's a wow. Complex of ZP modules, I guess the way I wrote it. You could get more, of course, but I mean, I just wrote down a site and, well, I sketched a site where you can take cohomology structures. So I'm going to write it here. Again, the definition is technical, but say the words at least. It's a Cartier-Witt divisor. Okay, and so I'm not going to again say all the conditions, and I'm also not going to. You have to take this quotient in an appropriate animated sense, but I'll just write it like that. So it's a derived scheme, this quotient, with a map to X. So that's why it lands in groupoids and not sets. Okay, so you have the Witt vectors of R. You have some kind of, it's called quasi-ideal here. And then you can form the quotient in some world of animated rings and take a map of derived schemes there. Okay, so that's again, I'm going to use it quite formally, but that's the definition of this. Was there things to check or conditions to impose? So maybe I'll say this is in some derived world. There's so Bob and Lurie, at least is where I learned it from. There's a relative theory. So if you start with a bounded prism, bounded p torsion, and some x to spec a bar, then you can form the following diagram. Fiber product. And what is this map here? Well, this is now a map of functors on the category of p-nilpotent rings. So I have to tell you where to send sort of an R-valued point. So that's a map from P to R.
Now you really want to say split.
Yes, I do. Okay, thank you. Yeah. What does it go to? Well, I have R, so I have bit vectors here. I'm going to R. So if I have a map like that, the universal property of bit vectors gives me a map from A up to a lift of that map. Okay, because I'm assuming that I'm starting with a delta ring here, that's a prism. And so I have a lift of Frobenius, so I get that map. And then, so you go to that, and then you can go to, I'll say, so that gives me an ideal, which is I extend scalars. And now that also gives me a map from A bar to W bar. And so, sorry, I wrote it badly. So you get R, then you get this quasi-ideal. You also get this map. So if you take spec, you get a map in the other direction. So spectrum from that to spec A bar, and let's see. Oh, and then I have to, so if I have a map from spec A bar to, sorry, up here. Oh, sorry, I'm just defining this map. So sorry, yeah, just defining that map. So that's it. That's all I need. All right, so that gives me a map from spec of this thing to spec. Okay, so that's the map. Sorry about that. Any questions about that? Okay, so then you define this to be the fiber product. And now, once you do that, read that, it's, and look at this setup here, it's of course, the natural thing is to put the stack here as the base, the log stack as the base stack. So we'll do that over here. Okay, so let's apply this. This A phi A. Well, there we can do the absolute theory or relative theory. So now the base prism will get replaced by the stack. And so maybe I'll start with the absolute theory. So that's X and X. It's a fine log scheme. Maybe possibly yeah, probably maybe fine log p-adic scheme, which I don't really need to worry too much about the definition of this. It's a map from the formal scheme to the stack, so I can do it just define it that way. And the fiber product and again, I mean, you have to do some work and I can write it out explicitly. So there's the final object, ZP prism. So a map to this thing is just a Cartier-Witt divisor. And so I take the fiber product of this diagram. Okay, now, I view everything as being kind of a relative theory. And I don't know if this is a good interpreter. I view this kind of as the final sort of prism. So that's why I think that's a natural thing to look at. Let me say what it is more concretely. So I have to plug in a p-nilpotent ring. So what is the data? So I have to give a map to this thing first of all, right? So I have to give a log structure. I also have to give a map to this thing, so I have to give a Cartier-Witt divisor. And now I have to give a map to X that's the map to here. But then I also have to specify that this should be over this base here. What is that saying? It's saying that if I have this log structure on R, I get a log structure on the bit vectors, which by taking the starting log structure and then taking the multiplicative lift of the bit vectors, taking the associated log structure. And so that turns out to be, well, and then you look at the regard. So that gives a map from the SPIF of the bit vectors down to a log structure there. And so then you look at the define the reduction, and what this arrow here you can think of as map. So that's kind of the concrete, more concrete interpretation. It's still not so concrete because this is some derived thing and so on.
Okay. Martin, can I ask
Yeah.
a question about the role of this object? So is this an object whose coherent cohomology would be the log?
It's coming. It's coming.
Okay.
Yeah. That's as far as I'll get. Yeah. Oh, sorry. Well, so I have to do the relative theory. A relative theory. So you can do this. So I hope you can guess how to proceed. Which is, so now we start with a log prism. And then again, you can form the diagram. And now the notation gets even worse, so apologies. On that, okay. So the same story, but now in the relative setting. So that would be I'm going to copy over from relative Cartier-Witt stack. In this context. Let's see, I think I don't have time to explain how you get the map, but if you follow Laurie prismatization of p-adic formal schemes, you will see that you get a map from the coherent cohomology of this thing here. To prismatic cohomology of, and I don't, you can think of, as I explained at the beginning of the lecture, you have various options for how you want to think about this, but it'll be, this is like Koshikawa's theory. And so you get a map there, which maybe I'll call star. So let's say theorem. Let's assume you can do better than this. But let me say this is the smooth case. It's log smooth. And star is an isomorphism. So you recover prismatic cohomology. So this is, and I should say the proof at this point, with all this setup, proof. Is descent. I mean, it's if your base stack here was actually prism, a ring, then we could cite your paper, and so it's taking a hypercover of the stack log and applying the set. Okay, so so you get that, and I guess one can work harder and get a stronger result without smoothness, some LCI or.
So what smoothness is unaffected in the property of the map from Max?
Yes, thank you. I should say I haven't, log smooth is equivalent to the map X to log bar and a bar. Sorry. So it really does feel like a smooth morphism over prism. Okay. Okay, maybe, let's see, I have 2 minutes. Maybe I'll just say, you can do the crystalline comparison in this way too. Well, maybe I'll just state the theorem. This is the case. The ideal is just and basically by descent. So we're in the case of the ideal is P here. You can define maybe I'll just state it. So you can define stacks, crystalline stacks, and so on. But let me just say, and using descent, they're really a correlate. Descent. Phi over star in the log smooth setting. Prismatic cohomology X and X. And this is out of time, so better not to. Well, but there, you can start working through the papers and getting arguments. Basically applying to set. So I think I'll stop there. Any questions?
I have a question on the star here. So I assume it's maybe it's not true, you can tell me, if the log structure is given by a normal crossing divisor, let's say, I assume you can assign a crystal in the log crystalline side, which would correspond to all of this divisor.
I haven't thought about that, but I think that's more about the map from the log prismatic side to the underlying side of the. I mean, you. The short answer is I don't know, but I think that would be more about investigating that map.
But here you don't have a divisor, you don't have the structure.
So the log structure would be the right to MX,
yeah.
and we're comparing sort of the log theory with the underlying ordinary theory.
No, I'm not sure, because the question was if it is really a crystal in the log prismatic side, then the star. I'm asking whether there is a Temnes theorem like the one of Pierre de Ligne, which says that the log prismatic cohomology of this crystal would be computed by the prismatic cohomology of the open, which is a complement of this.
Okay, yeah, that I don't know. That I
You don't know that.
Yeah, I see two hands, or three hands. I don't know, Jacob.
Is there also an approach to log prismatic F gauges from this log stack?
Well, I mean, this is, I hope, but I haven't done it. I mean, yeah. There was a part, section 5 of the talk, on the infinite root stack, which I think is what should connect it up to the Ital theory. And also related, I think, to that question.
So like for example, in your site theoretic your site theoretic homology, what you actually get, I think, is some like quasi-coherent sheaf over log of AMA, right? For a log prism. Does it really carry like more information? Or
I'm not sure I understood the question. Can you repeat it?
So in your site theoretic approach, you wrote like R gamma of X over some over log of A comma MA, right?
Yeah.
Yeah. So actually, I think you'll get some quasi-coherent sheaf over log of A.
Oh,
A
oh
comma
yes. I think that's an interesting thing to think about. Yeah. I mean, maybe it's easier to understand it just in the case when like simple normal crossing divisor, for example, because then it's really a map to the FAN modulo GM to the N. So you get something on there, sheaf. And so if you did, for example, A1 mod GM, that's like filtered complexes kind of. So you see something extra information there.
And also, I think it will be related to some like quasi-coherent sheaves over X comma MX prism. Right? But it's not clear what they are.
Yeah, I don't know.
I mean, something like RJ lower star, is that what you mean?
What's G?
So when you're taking the arguments from like the standard case and transitioning them into this log case, say for the crystalline comparison or similar, what would you say is the main technical difficulty?
Well, I mean, these are not easy papers. Can I say that? I don't know. You know, we all have our own things that are difficult for us. For me, it's, you know, all this derived machinery, but I don't know, for you, it might be something else. Is that a fair answer?
Like, I guess maybe I was asking, is there something that happens in the log situation that sort of doesn't happen in the usual case?
Well, it depends what you, I mean, what you want. I mean, these are rather, I explained some rather formal statements, which basically, I think, come out of dissent once you set up the machinery. Of course, if you want to say something more substantive, you have to really study these stacks more, and the geometry is more complicated because you're incorporating more stuff.
Okay, thank you.
Wait, sorry, so on that note,
Yeah.
is there any, what does this stack look like in the very simple example? Like take A1 and cursive
Yeah.
and log structure at 0.
Okay, can I do a slightly different one? Yeah, okay, and I think you might know the answer to this one already. I think you can help me with it, but let's let me, oh no, okay, yes. Let me do A1 FP with log structure defined by 0. First, we have a divisor. We have the line bundle coming from 0. So that's okay. So there's two ways you can do it. You can write down, in this case, what we're looking at is a map A1 P, right by 0, going to A1 P GM P Prism. Okay, and I think you can actually, as it's due to you, I think, write out the fiber product directly using the stack. Write down the stacks, but let me do it slightly differently. Okay, and let me just sort of give the moduli interpretation of, we're trying to calculate A1 ZP GM ZP. Sorry, for network ZP Prism. We're trying to calculate the fiber product of this diagram. Right, so what is it supposed to? You give me a p-nilpotent ring R, and I have to tell you what is the value on the fiber product, right? And so my R should come with a map to here. So I should have a, in this case, that's a line bundle mapping to R. That's sort of this factor here. And I'm supposed to have a Cartier-Witt divisor, but I want the reduction to map to be over FP. So in this case, this is going to be multiplication by P. Okay, so I get that. So that's given to me. And then what am I asking for? This is the universal torsor over here. So I have to, let's see. I want a trivialization but the reduction, let's see. Let's see, did I do this right? I'm a little worried whether that means ZP here. My notes are wrong. Let me do this one. Let me just take the. Sorry about that.
That's like much more complicated.
Is it more complicated? Okay. Sorry. Let's. Maybe we can talk about that. But what the answer should be, I think in this case, should be A1 ZP. Sorry, I'm getting confused at the board. GM, where GM is the kernel of GM ZP. Mapping to Prismatization. Let's see, and I think one can see this, if I stepped away from the board, just from interpreting it as line bundles and maps with appropriate trivializations of the reduction. Oh, sorry, now I see my mistake. This is not the zero map, that's the projection map. Not P, right? Right, so yeah, sorry about that. So let me read, since I bundled it, let me say it again. So you give map to here is a line bundle. The fact that the map on, so we are supposed to give a Cartier-Witt divisor, but the fact that it's supposed to go over FP means this has to be multiplication by P. And then we have to give a map to the universal GM torsor mod P. And so that's a trivialization of this here, of this module here. And so that's just, so that gives, right, so that corresponds to an element, if you allow yourself to cheat a little bit here, which is the point of A1, WR bar point of A1. And now you have to think about, well, okay, so if I started with a trivialization here, that's my map to A1. And then what is the group that acts? The group that acts is the group of automorphism, changes of choice of trivialization here that reduces to a given trivialization here. So that should be the kernel of this map. Okay, sorry for bundling it, but.
So I guess prismatization of a fine line over FP with no log structure is just a fine line over ZP modulo GA sharp. So is it, can you maybe, if you have this log structure corresponding to the point, maybe you need to take the quotient of by some subgroup of GA sharp. Is it possible to describe it this way?
Not for me standing at the board, but I would be happy to talk about it. Yeah.
All right, if there are further questions, let's talk about them over coffee.